Good morning, everyone. Am I audible?
Yes, ma'am. Good morning.
Yeah. Okay. So let's start in 5 minutes. Can anyone tell me how far you have done in week 10?
Ma'am, 10.4 and 10.5 was left.
Okay, so view serializability is done, right?
Yes, ma'am.
And did you start any of the recovery part, cascadeless schedule, those things?
Yes, ma'am. Yes, the ma'am was.
Ma'am,
Okay.
briefly, can you please touch upon it also? Briefly, not too much.
Recovery, right?
Yes, ma'am.
Yeah, okay, sure. So today we'll discuss first, let's recap that recovery part. Then 10.4, 10.5, mainly we have locking protocols, right? Concurrency control. So we'll do the locking protocols, two-phase locking. Mainly we have two-phase locking only, and timestamp protocol. Okay. All right. Let's wait for 2-3 minutes more. Other people will join. Then we'll start. Okay. So let me ask a few questions since serializability is discussed. So anyone tell me what is a serializable schedule?
Ma'am, any schedule that is consistent on commit and which can be rolled back, maybe it's called serializable.
Okay. So okay.
Rather, which
So,
follow those four properties, this asset properties.
right. Acid properties. So what is in acid properties? What is consistency? Anyone? What are the four acid properties?
Atomicity, consistency, isolation, and durability.
Right. So we need to know the definitions for all four of these, right? Atomicity means what? That every schedule will be every transaction or every, what can I say? Okay, let's say transaction. If we have two transactions T1 and T2, when can I say that they are both following this atomicity rule? So
Ma'am,
atomicity means that yeah, go on.
sorry. What I understood from atomicity is that it's either the transaction occurs or it doesn't occur. I mean, there is
Yes,
no in
right.
between.
Yes,
Yes, that's the correct definition. So either it occurs or it doesn't occur. So no transaction will go halfway, right? So next is consistency. Consistency means what? No matter what happens after the transaction is done, the database should be in a consistent state. Like if, let's say, if I have 500 rupees and there are two people A and B. Okay, so I want to transfer 500 rupees from A's bank account to B's bank account. So initially B has 0 rupees, A has 500 rupees. So my total sum is 500, right? And after the transaction also, so what should happen? That now 500 has been transferred from A to B. So now A has 0, B has 500. So the total sum remains 500, right? So this is
yes,
consistency. That total sum before and after the transaction should always be same. So if in some schedule, if something goes wrong, that even sometimes this can happen, that even if I sent 500 rupees from A's to B's account, but still in A's account it is showing that 500 is still there. That means that the database was not updated, but now the total sum is 1000, so that is not equal to the initial sum, right? So this is violating consistency. Isolation is what? That if there are two transactions T1 and T2, okay, so they should act like they are not dependent on each other, right? So they should be working independently. That is isolation. And durability is the easiest property. That means whatever changes we are making to the database, those should be permanent changes. If I'm committing some change, then that change should stay, right? It should be persistent. not like after an hour the change goes back to whatever it was before. That is durability. Okay, so these four are the most important properties. So remember the definitions also. Now, two types of serializability we saw: conflict and view, right? So conflict serializability, how what are like how can you check whether a schedule is conflict serializable or not? Anyone, can you tell me what is the method of checking?
Then we try to make a topological sorted graph.
Right. So first, what do we need to do? If I have
First, we
say
need to make the
Set
schedule, ma'am. Schedule.
right
The the chronological order in which it will rather
the
where
read
it is
write sequence.
conflicting, yeah, and where it is
Yes.
conflicting. According to that, we need to draw the graph, the
So what are
precedence
the
graph.
conflict? What are the conflict operations?
if there is a write and read in different transactions.
So it is read write read, and write write. These three are
Yeah.
conflicting, right? And only conflict occurs when these operations are happening on the same variable, right? And read is the only operation that does not cause conflict. So conflict happens when on the same variable read write operation occurs, or write write operations occur, or write read operation occur in two different transactions. Okay. So this is first you have to check this, that what are the conflict operations. Then you draw the precedence graph, right? Precedence graph, how will you draw? So if there is a conflict from transaction T1 to transaction T2, then there will be an edge from T1 to T2 in the graph. What are the nodes of the graph? How many transactions you have? Those are the nodes, right? Now in a precedence graph, if there is a cycle present after you have marked all the edges, if there is a cycle present, then is it conflict serializable or not?
No, ma'am.
No,
No,
right?
ma'am.
So the rule is CNC, that is cycle not conflict. That means if it is if cycle is present, it is not conflict serializable. Okay, so this is just a short acronym we use. Now after this, if I ask you that what are the equivalent serial schedules, how will you find that? So for that you have to do the topo sort, right? So how is topo sorting done? Anyone?
And
How do you start?
the node with 0 in degree will be first node.
Right. Then
Then the out degrees from that will be removed. That node will be removed. So the next node which has 0 in degree will be the next node, and so on. We can topologically sort.
so we always have to make sure that if there is an edge from say transaction T1 to T2, then in the topo sort T1 should always come before T2, right?
Yeah.
So after you are done with topological sorting, so if it is a conflict serializable schedule, then there can be more than one uh, equivalent serial schedules, right?
Yes.
Those things you know how to find now. View serializability. So if a schedule is conflict serializable, can I say it is view serializable?
Yes, ma'am.
If it is view serializable, can I say it is conflict serializable
No,
also?
ma'am. No, ma'am.
So which is the bigger set, view or conflict?
Conflict.
View serializable is the
View
bigger set,
serializable is the big.
because every schedule that is conflict serializable will also be view serializable, but any schedule that is view serializable may or may not be conflict serializable, right? So what is the procedure for checking for view serializability? Let's say a transaction is not conflict serializable, then how can I check if whether it is view serializable or not?
There are blank writes then.
Blind writes, right? That
Ma'am,
means,
Blind.
could you please repeat view serializable?
sorry sir, you're not audible.
Ma'am, could you please repeat view serializable?
Okay, view serializable. Okay, see, first thing is that view serializable. First, you will do what? If a schedule is given to you, you will check whether
Ma'am,
it is
you are
conflict.
sharing the screen.
No, 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 I'm not. I'll share. Wait.
Ma'am, there
So,
is a question in practice assignment which is asking number of view serializable options
yeah,
for.
number of views realizable actually won't be asked. It is a difficult question. Okay. First of all, like checking for view serializability. Like, okay, let me tell you, it is an NP hard problem. Okay, so mainly what type of question we will ask right now is that whether a schedule is view serializable or not. Okay, so mainly checking for that is what you will do. First, you have to check that whether it is conflict serializable. Okay, if it is conflict, then very good, it is automatically view serializable. If it is not, then you have to check certain conditions for view serializability. What are those conditions? First, you have to check what are the initial reads on each variable, right? Then you have to check what are the final writes and the write read sequence. So if a schedule has blind writes in it, okay, then it will be view serializable. Blind write means what? That I am writing on a variable without reading it. Okay. Okay, let me share the screen. Is it visible?
Yes, ma'am.
Okay, so these things are done with. Right. I think I don't have the slides for view serializable. Just a second, huh? Because I was told that it is discussed, so I didn't keep it here. Wait.
Ma'am, will you be taking doubts in PA questions, ma'am?
I have a lot to discuss. Okay, first let me finish the week 10 content. Then, if we have time, actually, I don't think we'll have time because I have a meeting from 11:30. So, let's first try to finish all because there is a lot of content this week. If it is not possible, you have TA sessions before the deadline. Do you have?
Today is the deadline, ma'am.
Oh, today it's the deadline. So, do you have any TA sessions today after this class?
No.
No, ma'am.
All right. So, I'll try to take, if there is time, I'll take doubts. Otherwise, you can post on Discourse, okay, and tag the TA and us. Just a second. Let me find the slides. Okay. You can see this. View
Yes.
serializability. Okay. See. So two let S and S dash are two schedules with the same set of transactions. Okay. So S and S dash are view equivalent when conflict equivalence. That was discussed. Conflict equivalence. Anyone? Okay. I will.
No, ma'am,
I
it was
hope
a
that was discussed.
the equivalence part. If it is conflict serializable, then it is conflict equivalent, right?
When are two schedules conflict equivalent? Those things that was discussed.
No,
Ma'am,
ma'am, the equivalence part was not. I don't think it was discussed.
Okay,
is
just
there
do
any
one thing. If I start discussing this, this will take a lot of time. Just do one thing. Go to my previous turn's live session. Okay, there it was discussed. So just go through that once.
Ma'am,
I'll start
in
with
any of
view.
the previous terms live session, do we have PA questions discussed, ma'am?
PA question, see, week 10 actually falls at a time when we have this quiz to OPA, all these things. Okay, so last term also we got only one session. I think the term before that, PA question was discussed.
Oh, in
Okay, so
January.
last term, yeah, Jan term, I think PA was discussed.
Okay, ma'am.
Ma'am, can you give
Even
a high-level overview on what that is, the equivalence?
equivalence, for equivalence, you just have to check what is the sequence. Okay, like the write, read, these sequences. If I could discuss it a little, it would be good. Basically, it should be conflict equivalent to a corresponding serial schedule. Then it is called conflict equivalent. See, if a schedule S can be transformed into a schedule S dash by a series of swaps of non-conflicting instructions, then we say that S and S dash are conflict equivalent. So this thing, have you done this swapping, read write swap?
Yes, ma'am.
Yeah, this is only
Yes, ma'am.
conflict equivalent. Okay, so if
Yes, ma'am.
by
This we have
doing,
done. Yeah, this we have
yeah,
done.
yeah, so by doing this, like on a schedule S, by doing swaps of read and write, if you can achieve a serial schedule S bar, then these are conflict equivalent. Okay, that's all. Now view equivalent is what? If there are two schedules S and S bar, okay, with the same set of transactions, then S and S bar are view equivalent if all these three conditions are met for each data item Q. So initial read is what? If in schedule S, transaction Ti reads the initial value of Q, then in schedule S bar also, transaction Ti should read the initial value of Q. That means, let's say this is a schedule. Okay, so this is schedule S. Under this, there is transaction T1 and T2. Okay, so if in S, T1 makes the first read operation on variable A, then in S bar also, T1 should be the one making the first read operation on A. It shouldn't be T2. If T2 does the first read, then there only we can say that they are not view equivalent. Okay. Now, this is the first thing you have to check for every variable. So if there are two variables A and B in schedule S, then you have to check what are the transactions that are performing initial read on each of the variables. Those same transactions have to perform initial read on each of the variables in S bar also. Okay. Second condition is write read pair. So if in schedule S, let's say transaction T1 executes read of A. Okay. Then that value that was produced, see this. If in schedule S, transaction Ti executes read Q and that value was produced by transaction Tj. That means if in this schedule S, let's say Ti or T1, okay, performs some write operation on variable A. And after that, T2 was reading this value, which was updated by T1. It was reading this updated value. Then this is a write read pair, right? So T1 updates the value and that updated value is read by T2. Now this write read pair should also be followed in S bar. That means in S bar also T1 should make the write and that updated value should be read by T2, not the other way. If it is like that T2 is doing the write and T1 is reading the updated value, then that is wrong. So this write read pair should also be same. See, then in schedule S bar also, transaction Ti should must read the value of Q that was produced by the same write operation of transaction Tj. So write read pair should also be same. Last condition is final write. Final write means transaction that performs final write on variable Q in schedule S must also perform the final write on variable Q in schedule S bar. That means final write means the last write operation. In schedule S, if the last write operation on variable A was done by T2, then in S bar also that final write should be done by T2 only. Okay, and these things you have to check for every variable in the transaction. So these 3 points are clear.
Yeah, ma'am.
Yes, ma'am.
Okay. So if you can see that this works for S and S bar, all 3 points are satisfying, then I can say S and S bar are view equivalent. Okay. So view equivalence is mainly based on what? Purely on reads and write operations. Now, a schedule S is view serializable when it is view equivalent to a serial schedule. Okay, that means if I have, let's say, a concurrent schedule S, concurrent means that there are two or more transactions which are occurring simultaneously, right? So if there is such a schedule S and it is view equivalent, that means all those three conditions that we discussed, those are all satisfying with a corresponding serial schedule. Serial means first T1 will occur, then T2 will occur, then T3 will occur, like this. That means they cannot occur simultaneously. So if it is view equivalent to such a serial schedule, then I can say that serial schedule S is view serializable also. So every conflict serializable schedule is also view serializable. Okay, so this is one schedule given. So it is view serializable but not conflict serializable. So this is possible, right? That a schedule can be view serializable but not conflict. But if it is conflict serializable, it has to be view serializable. So what serial schedule is the above equivalent to? So if I say that this is view serializable, that means I am definitely saying that it is view equivalent to some serial schedule, right?
Yeah.
So what is that schedule? That is, what serial schedule is this equivalent to? How will you find that? Look at the operations. Okay, so T27, T28 and T29, this is the serial schedule it is equivalent to. So how can you check whether this is correct? So first check what is the initial read. So if I do this, if I write the serial schedule, so this is T27, T28, T29. So if I write this serially, then first read of Q here, then write of Q, right? T27 is over, then write
Yeah.
of Q, then write of Q here. This is the equivalent serial schedule. Okay. Now
Yes.
check for those 3 points. So initial read on Q is done by which transaction in schedule S? 27. Here also
Yeah.
27 is doing the read. Who is doing the final write? 29. Here also
29.
29 is doing final write.
Yeah.
Now check write read sequence. Sorry. Yeah, write read sequence. So is there a write read here? After the write operation is
No.
performed,
No,
is
ma'am.
there
No,
any
ma'am.
read? That means you don't have to check. So these
Ma'am,
are,
could you please explain again?
see, this is a given concurrent schedule, right? I am saying that this is view serializable, but not conflict serializable. So if that is the case, that means this schedule has to be view equivalent to some serial schedule, right? View equivalence, we just saw those 3 points we have to check. So they're saying that it is view equivalent to this schedule, T27, then T28, then T29. This is the equivalent serial schedule. So if I write that serial schedule, it will look like this, right? Serial schedule means what? First one transaction will totally complete execution, then another transaction can start. So if I'm saying that this schedule S bar is view equivalent to this schedule S, that means those three conditions have to be met. So first condition is initial write. So in S, who is performing initial write on Q? Transaction T27, right? In
Yes, ma'am.
Initial read,
S
na ma'am.
bar, initial read,
Initial
I'm
read.
sorry, initial read. Then in S bar also, initial read is performed by T27. Who is performing final write on Q? T29. Here also T29 is performing final write. Now check that after a write operation, is there a read operation on the same variable Q? No, right? So after these three writes, there are no reads. There is only one initial read. So I don't have to check for that write read sequence. So what are these writes called? These are blind writes. Blind write means, see, these transactions T28 and T29, did they ever read the value of Q? No, but they are directly writing. That means if you update a variable without reading its current value, then that is a blind write. Okay, and every view serializable schedule that is not conflict serializable will definitely have blind writes. It has to, right? So if easy way to check is what? If you see that a schedule is given to you, I'm asking whether it is view serializable or not. First, you will check for conflict serializability. If it is conflict serializable, you know it is view serializable. If it is not, then next step is that you have to check whether it has blind writes. Okay. So mainly what will happen is if a blind write is present, that means that will be view serializable. Still you check the conditions. Okay. You check that is there a serial schedule that exists that is view equivalent to this one, right? So if you can form such a serial schedule which is view equivalent to your current schedule, then it is definitely view equivalent. But the important thing here is that every view serializable schedule that is not conflict serializable will have blind writes in it. If it doesn't have blind write, it won't be view serializable. So one more way that you can check, let's say a schedule S is given to you which is not view serializable. So how can you be sure of that? First, it will not be conflict serializable. After that, check for blind writes. So if you directly see that there are no blind writes, that means you can say that it's not view serializable. You don't need to check the other conditions. But if it has blind writes, then you need to check. Okay. Is this clear?
Okay, ma'am.
Yes, ma'am.
Ma'am, how do you arrive the S dash?
See, S dash, so what are the possible serial schedules that can occur? So you know that if you need a schedule which is serial schedule which is view equivalent to this one, so what are my conditions? That initial read should be same. So first you check in S which transaction is performing initial read. So that has to come first. So T27 has to be the first transaction. Who is performing the last one? Last write? That is T29. So it has to be in the last. So T29 will be the last one in your serial schedule. Then T28 is only left. Right. See, and like arranging the serial schedule is not a big deal. The big thing is that you have to check for the blind writes and you have to check that all three conditions are met. But if you directly see that there are no blind writes, then you can directly say that it is not view serializable.
How the read in T27, how read of Q is, I mean, write of Q is next to read of Q, how that arrangement happened.
Ma'am, even I had this doubt. Like, see, if in Schedule S, it's not
Hmm.
conflict serializable because when we do the like when we draw the graph, precedence graph,
Precedence graph,
there
there
is a
will be
cycle.
cycle. Yes.
There is a cycle. But
Yes.
when you do the S dash, when you come to S dash, that cycle is removed, right? So it is
Because
conflict serializable.
every serial schedule will always be conflict serializable. Conflict serializable or not, this question arises when we have a concurrent schedule. Right.
Okay.
Serial schedules will definitely be conflict serializable. Serial schedules don't have any issues in them because first a transaction is over, then the next transaction starts. So all
Okay.
serial schedules will be conflict serializable. That is why we are
Okay.
trying to find the equivalence between these two.
Equivalent.
That if
Okay.
it is,
Okay.
yeah, if it is
Okay.
equivalent to a serial schedule, then it is definitely conflict serializable or view serializable.
Okay.
Okay.
And ma'am, one more thing that when you swap that right queue, like just like Suresh sir asked, that right queue you have
Hmm.
swapped it, right? So, but basically we
Hmm.
swap only when there are no conflicts, right? But here there is a conflict, right queue and right queue, there is a conflict, right? So how are
Look,
we?
it is not basically a swapping. Okay, I'm not doing a swapping. uh, if you think of it as a swapping, see how I want to explain this is I am finding a serial schedule which will be equivalent to this one, right? So what are my conditions? I first know that for it to be view equivalent, then the first read operation should be on the same transaction. That means T27 should perform the first read, right? So T27 should
Yes.
occur first. So
Yes. Yes.
I am forming a serial schedule. Serial schedule means what? T27 if it starts, it will end first. Then other transactions can occur.
Okay. It's just for represent. It's not actual
Yes.
swapping that you've done.
No, no,
Okay.
no. It's not
Okay.
actual swapping.
So it's a
Okay. So I
serial
am just
schedule. Okay, S
yeah, I'm
dash is
just
a serial.
finding an equivalent serial schedule. So first T27 I got that way that okay, this read has to be in the same transaction in the equivalent schedule. So first T27 occurs. Then final write is happening in T29. Then definitely T29 has to occur at the end. And only T28 is left, so it will occur in the middle. Right. This way you just find a schedule. Main thing you have to check for is blind writes. Blind write makes it very easy to check because if there are no blind writes, you don't have to check any further. You can say it is not view serializable. Okay. This part is clear. Can we go to recovery now?
Yes, ma'am. Yes.
Okay. So recovery is what? See, serializability helps to ensure isolation and consistency of a schedule. Isolation means they're independently occurring. Consistency means whatever changes we are making, right? so that doesn't leave the database in an inconsistent state. Yet atomicity and consistency may be compromised in the face of system failures. So if there is a system failure in between your transactions, like if during your transaction is happening midway, there is a system failure. So at that point, the transaction couldn't commit or couldn't complete. So that can be a state in which the database becomes inconsistent, right? And it is also violating atomicity. Why? Because atomicity means if a transaction starts to execute, it has to complete, cannot leave midway. But system failure can give rise to these two violations. So you consider this schedule, it is comprising of a single transaction. Okay, so single transaction means obviously it is a serial schedule. So first there is a read on A, then I'm subtracting 50 from A, then write, then read B, add 50 to B, write B, then commit. Commit means we are making the changes permanent. Now, what if system fails after step 3 and before step 6? That is, after this write of A is done and before this write of B is done. So between step 3 and step 6, if somewhere the transaction fails or the system fails, then it can lead to an inconsistent state, right? Because see, initially, if I say that A has 50 rupees, okay, if I say A has 50 rupees initially and B has 0 rupees, so what is the sum initially? 50. Now, after this step 3 is done, that is 50 rupees have been deducted from A. Currently, A has how many rupees then? 0 rupees.
Zero.
B also at this step 3, B also has 0 rupees. So now the sum is 0. Now, if the transaction fails here, that is the 50 rupees were never added to B's account. So what is the initial sum and what is the final sum? 50 and 0, are they matching? No. So this is inconsistent, right? So this type of things can happen when system fails in between a transaction. It can lead to inconsistent state, and now what we need to do is we need to roll back. Roll back means whatever changes we have made so far, we need to undo them. So I will roll back to step 1 where I was starting the transaction. So this rollback procedure, this is known as recovery. Okay, so I'm trying to recover a transaction that was stopped midway due to some kind of failure. So if a transaction Tj reads data item previously written by a transaction Ti, then the commit operation of Ti must appear before the commit operation of Tj. So this is how we make sure that recovery is possible. So we don't work with one single transaction, right? There are multiple transactions. So if there is a concurrent schedule with two transactions, let's say T8 and T9. Okay. Now, let's say T8 is writing some or updating some variable. So let's say it is performing a write of A. Okay. And after that write of A is performed, that updated value of A is being read by T9. So that means there is a write read pair from T8 to T9, right? T8 updates the data, then T9 reads that updated data. Now, if the commit of T8, see, if the commit of T8 doesn't occur before the commit of T9, then it will not be a recoverable schedule. Why? Because here in this example, see, so first T8 is reading A, then it is writing A, then T9 this read A. This A is what? This updated value. This it is reading na here. Whatever T8 updated, that value is being read here, right?
Yes, ma'am.
So if the transaction T8 before T8 commits, if I commit T9, okay, so I committed T9 here. After this, let's say some failure occurred. So this will not be a recoverable schedule. Why? Because this change has already been committed to the database. Right? That means T9 has already read the updated value which was not committed. So at this point, if a failure occurs here, after this commit is issued, if a failure occurs, that means this updated value, was this ever committed to the database? This write of A,
No, ma'am.
this was never committed, but this value was read by some other transaction which performed a commit, right? So this is a wrong thing. This will hinder your recovery. So what is the proper step for making sure that your schedule is recoverable is that if a transaction Ti reads some data which was written previously by transaction Tj, then commit of Tj should appear before commit of Ti. That means T8 should commit before T9 commits, right?
So ma'am, if this commit comes before this read B, suppose read A, write A, then commit A. After that, if T9 that is read A, then it is recoverable.
See, basically, commit occurs only once in a transaction, right? So commit will come at the end. Okay, let's say commit comes here. Here if I commit and this commit was not here. Okay, after this, if some system failure occurs, then it will be recoverable.
Okay, ma'am.
Okay, basically, the transaction who is updating the data, who is doing the write operation, they should perform the commit first. Okay, not the transaction who is reading the updated value. Because if the updated value is not committed, then what are you, if you're reading such an updated value which was never committed, then that is a wrong value. If the system failure occurs, then that value will never be committed to the original database. That means that value doesn't even exist in the database, yet you have read that value and committed your transaction. That is wrong. The transaction which performs the write has to commit first, then the transaction that reads will commit. So this is basic step for recovery. Now T8C.
Ma'am,
For
ma'am,
yeah,
ma'am,
yeah.
one doubt. Sorry. If the error occurs before read B and you've committed after that, then there is no issue. It will be rolled back, right? Because there is no then the values of A have not been committed, so it is easy for rollback. But if the error occurs after the commit in T8, there is no commit in T9 now, but there is only commit at the end of after read B, and after committing in read T8, there has been an error. Then will it roll back to the original state?
Like
No.
after this read B, you're saying this commit has
Yeah,
happened,
commit has occurred and then there is an error.
but T9 has not committed.
No, no, T9 has not committed.
So if there is an error, then you can roll back T9, right? Because it has not committed.
But
Error will occur when
T8 we cannot roll back, right?
no, that you have committed, that you cannot do anything.
Okay.
Error will occur when you have read such a value which was not committed and then the system failure occurred. But you have already committed in the transaction in which you are reading the value. Okay. So the
Ma'am,
following.
Okay, ma'am. Yeah.
one
So that
question.
transaction will not be rolled back. Wherever it is committed and then the error occurs, it will not be rolled back.
No.
Okay, okay.
Ma'am, does commit have a significance of a read after a read?
Yeah, like if let's say your transaction only has a read operation. Okay. So you just perform that operation and do the commit. But yeah, it will definitely not be reflecting any changes in the database because it is just a read. Right. If it is a write, then only the changes are made. Read
Oh,
means you're just reading a value. So
oh,
it has no real significance, but yeah, if that is the only operation that is present, then you have to commit after that.
okay.
But every transaction should have a commit. Now, see, the following schedule is not recoverable if T9 commits immediately after the read operation. If T8 should abort, that means if it is not completing, if T8 does not complete, then T9 would have read and possibly shown to the user an inconsistent database state. Right. So if let's say your transaction in ATM, sometimes we can ask to see our account balance, right? So in that case, let's say T9 is such a transaction which is trying to show us the account balance. So it just has to read the value, right? Now let's say T8. Okay. A good example will be if let's say my account has 2000 rupees. Okay. So first T8 is the transaction that is reading this 2000. Now I have withdrawn 500 rupees. So what is the current balance? 1500, right? If I have withdrawn 500. So now the write A, it will write the what is the changed value it will write? 1500 in my account. Okay.
Yes. Yes.
Now this 1500 is read by T9. So I ask to see what is my account balance. So T9 is that transaction. It is trying to show me my account balance. So it will read 1500. Okay. Then it commits. That means it will show me this value. But somehow my transaction failed. That is, this 500 rupees was not properly debited or it was not transferred. This can happen, right? Some kind of system failure happened, the transaction didn't occur. But this already showed me the value 1500. in my account. So this is wrong because this 1500 value doesn't even exist in the database. This never happened. So it just read an intermediate value which was not committed and it showed it to me. This is the error. Okay. This is an inconsistent database state. So a database must ensure what? That all schedules are recoverable schedules. Is the concept clear? What is recoverability?
Yes, ma'am.
Now we come to cascading rollback. Now this is a very important thing. Okay. Cascading rollback is what? A single transaction failure that leads to a series of transaction rollbacks. That is, the changes are cascaded, the errors are cascaded. This happens when, consider this scenario. So T8 is a transaction which first read the value of A, then read the value of B, then made some changes to A. So a write A is performed. Now this write A, after this write A, the updated value of A is read by T11 and then T11 performed some write on that, that is updated the value further, which was read by T12. All these things happened. Now T10, if after this T12 read is done, after that if T10 aborts, that is it cancels this transaction, doesn't complete. So T10 is failing means T11 will also fail because this read A was performed based on this write. And if T11 fails, then this T12 will also fail because this read was performed based on this write. So because of one transaction failing, if a series of transactions fail, that is because of one transaction failing, if a series of transactions have to be rolled back, then that is called a cascading rollback. Okay, it can lead to the undoing of a significant amount of work. So this is a very simple schedule, but in real time, the schedules are much larger. They have a lot more of read write operations. So cascading rollback can be very expensive, right? If just for one mistake, one transaction not completing, a series of transactions are getting aborted, then that is a very expensive mistake. This cascading rollback, is it clear when it happens?
Yes, ma'am.
Okay.
Ma'am, one question here. So I mean, I'm trying to understand the rollback of a read transaction, actually.
Yeah, see, rollback of any transaction means that you are just going to undo that. Okay, go to the first step where the transaction started. So in T12, there is only one step, read A. So this read will be undone. That means you are, let's say, here A was initially 1000. Okay, B was whatever, I don't care. Then A was changed to, let's say, 800 here in this write A. Then this 800 value was read here, right? And then some changes are made. Let's say now A becomes 500. Now this 500 is read here. So if this transaction fails, T10 fails, none of these are committed at this point, right? So if T10 fails, then this write will have to be rolled back. So this 800 value now doesn't exist if it is rolled back. So that if 800 doesn't exist, then this read also cannot occur because it is reading a wrong value, inconsistent value that doesn't exist. Similarly, if this doesn't exist, then this 500 also doesn't exist.
Okay,
So
so
all of them have to go back to the first step.
all these transactions get cancelled, and whichever triggered these transactions won't get the data as it expected.
No, nothing will happen
Okay.
because T10 fails, all of them will fail.
Okay.
Okay. So cascading rollback is an expensive mistake. Now cascade less schedules are what? So for each pair of transaction Ti and Tj, if Ti and Tj are two transactions such that Tj reads a data item that was previously written by Ti, then the commit operation of Ti appears before the read operation of Tj. Okay. See, read it very slowly. So Ti and Tj are two transactions. Now Tj reads a data item that was previously written by Ti. So like here, Tj is T11, which is reading data item A, which was previously written by transaction Ti, which is T10. So this wrote the last value of A, which was read by T11, right? So in this case, the commit operation Ti must appear before the read operation of Tj. That means before Tj, that is T11, can read this value, T10 should perform a commit here. If I can make sure that this is the case, then I can make sure that cascading rollback will never happen. It will be a cascadeless schedule. Why? Because now, see, after this commit, if the system fails, do I need to roll back T10? T10 was
No, ma'am.
committed,
No.
No,
right?
ma'am.
So these changes were committed. After this, whatever happens, not my problem. I can just roll back T11 and read the value of T10 again, because this was committed to the database. So to make sure that cascading rollback doesn't happen, the one thing you have to make sure is that if Ti is writing some data item's value which is read by Tj, then before that read happens in Tj, Ti should be committing the value that it changed. So if Ti performs its commit before Tj performs its read, then it will be always a cascadeless schedule. Okay. Every cascadeless schedule is recoverable. So we can recover any schedule that is cascadeless. So it is desirable to restrict the schedules to those that are cascadeless. So we always want schedules which are cascadeless. Okay. So here, this is a schedule which is not cascadeless. Why? Because, see, after this write happened, there is no commit, but this read happened before any commit. So this is a cascadeless schedule. If there was a commit operation here after which this read happened, that would be a cascadeless one. Similarly, if there is a commit operation here after which this read happens, then it will be a cascadeless operation. Okay. See, this is an irrecoverable schedule. Why? So first, see, A was 5000. Okay, A's value in database is initially 5000. Then T1. So T1 performs a read on A. So when it performs this read, what is the value it is reading? 5000. Right?
Yes, ma'am.
Initial value. Then 1000 is deducted from this. So now A's value is 4000 and it is writing this value. So A is 4000 at this point. So there is no commit here, right? No commit in T1. But T2 starts. So T2 is now reading this value. What value is T2 reading? 4000. But see, in the actual database, okay, the commit has not been made. So these are what? Temporary changes, right? As long as you are not committing, no change is permanent. So this 4000 is now being read by A, then this T2, then some 500 is added, which makes the value 4500, and then it is written back and then it is committed. So T2 is committing before T1. After this commit, at this point, what is the value in database? 4500. A's value in database is 4500, right? Now if a failure occurs here, then what will happen? That is before the commit of T1, if a failure occurs. So is this a recoverable schedule?
No, ma'am.
No.
Because this read was performed based on this write, which was never committed. So this is an irrecoverable schedule because this commit happened. If this commit had not happened, then it would be a recoverable schedule still. But this happened, so now it is not recoverable anymore. So rollback is only possible till the commit of T2, right? I can only roll back a transaction that has not committed. So the computation of A, 4000, and write in T1 is lost. That is, this 4000, this write, was never made, right? So if this write was never committed to the database, then none of this matters. This 4500, these things, they won't work because this change was never made. So this is an example of an irrecoverable schedule. Because here Ti, which made the write operation, and Tj made the read operation. But Tj committed before Ti committed. So this is irrecoverable. This is a
Ma'am,
recoverable.
ma'am, what if the failure point comes after T2 commit?
Yeah, that is what happened. T2 committed, then failure happens here.
No, failure point is at T1. What I'm saying after T2, under that T2 commit.
No, failure means failure. System failure means system failure, not individual transaction failure.
Doesn't matter where it is. Okay, fine. I misunderstood.
Here, failure point means the entire schedule is failing. That is, this transaction, the system failure occurred, so T1 didn't commit. Okay, but T2 has already committed, so there is nothing to do here.
Okay, ma'am.
But if,
Clear, ma'am.
okay, so this is an example of recoverable schedule. See why this is recoverable. So first, 5000 is in the database. T1 performs read, 1000 is deducted, write A. So at this time, in T1's buffer, 4000 is present, and in the database also this change is made. But this is not a permanent change. This is not a durable value because commit hasn't been done yet. Next, T2 is starting the read operation, then adding 500, write A. So 4500 in the database at this point. But none of the transactions have committed yet. Right? At this level, none of them has committed. So after this, if the failure occurs, where none of the transactions committed, so now can I roll back both transactions?
Yes.
Right? Because none of them have committed. So first I will roll back T2, then I'll roll back T1. So all the changes can be rolled back. So this is a recoverable schedule. If this commit had happened before this failure, then it will not be recoverable. Understood?
Excuse me, ma'am. I had one doubt. Earlier, when we saw somewhere abort function, abort and failure, they're all same, right?
Yeah. Same thing. Abort
Okay,
means
but
you
I,
are canceling the
yeah,
transaction, and system failure is some kind of failure that occurs on its own.
okay. So in that point, actually, it was my understanding that if it was below T1, then the T1 can be rolled back because there is no commit below T1. It's not
Yeah.
like that, is it? It's like a full the T1 T2 transaction both get a failure.
Yeah, like
Both get aborted.
when we talk about recoverable, it is not about individual transactions. It's the entire schedule. So
Okay,
even if
okay,
one transaction is not recovering, one transaction cannot be rolled back, then the schedule is not recovering.
okay, got it.
So this is one without cascading rollback. Same thing only. See why this is without cascading rollback. That here rollback is possible without cascading wherever failure occurs. Why? Because after this write was performed, there is a commit. After that, the read is being performed. So this is how we make sure that cascading rollback doesn't happen. That is, after every write operation in a transaction, there is a commit. Then the next transaction can start its read. So this one will definitely be recoverable always. Now,
Ma'am, excuse me, ma'am.
hmm,
Ma'am, in the above example here, so if this read operation, it was before the commit, uh,
then it is
what?
not recoverable. That means I cannot say that it is. It can be recoverable, but I cannot say that it is. It will not have cascading rollback. For sure, I cannot say that. So if this read operation happens before the commit, and then there is some kind of system failure, then it will not be. Then cascading rollback will happen. That means T1, T2, all of them have to be rolled back.
Okay. What I'm saying is, ma'am, this read operation is above the commit line, and
Hmm.
after it is committed, and then the rest is same. Like, uh,
So
A
you're
is
saying
up
that
to
this read is happening here
correct.
somewhere
Correct.
before the
Yes.
commit,
Yes, ma'am. Yeah. Yeah.
but this
The
commit
rest are
happens.
same. Yeah.
Okay. So after this, if the commit happens, then it is all fine. But if the commit doesn't happen, then it is not recoverable.
Okay, but if commit happens, it is recoverable.
Yeah. If both transactions commit is happening, then I can recover, right? When the question of recoverable arises is when there is a system failure. If there is no system failure and all transactions are committing, then I'm fine with it. But our what we are trying to do is we don't know when system failure will occur, so we have to take preventive measures. The preventive measure is that if some transaction T1 is updating some value of a variable A and T2 is reading that updated value, so before T2 reads the updated value, you commit that T1 transaction, so that in future if there is some kind of failure also, we can recover the schedule. Okay.
Okay. Okay.
Okay. Now see, these are some just a second. So these are some transaction control language commands. So commit is one such command that you saw. So commit is what? It is the transactional command used to save changes invoked by a transaction to the database. That is whatever changes we are making. To save them permanently, we use commit. right? So commit saves all the transactions to the database since the last commit or rollback command. Now syntax is what? Just commit. That is the syntax. So if let's say in some database I'm trying to perform some uh, delete operation. So this is my table, original table. Now I am saying delete from customers where age is 25. So all the rows where age is 25, those will be deleted. And then I'm saying commit, that is commit these changes to the database. So what will the database look like after this? After the commit, it will look like this. So this row 2, row 4, these two are deleted because age was 25, right? Rollback command does what? That rollback is the command used to undo transactions that have not already been saved to the database. So rollback only happens when. So this can only be used to undo transactions since the last commit or rollback was issued. So syntax for rollback is what? That delete from customers where age 25, this I did. But see, this change is not committed, right? After this delete statement, is there a commit? No. There is a direct rollback. So I can undo this. So this was the original table. Then I did this delete operation. Then I did a rollback. So if I do rollback, after rollback, it will look like this only. That is the same thing. So I am undoing all the changes that I did, right? So the delete operation that I performed is undone. So it will give me back the same table. This is commit and rollback. Now this is very important because there are numericals on save point. Okay. So what is save point? Save point is basically, see these rollbacks that we are doing, right? So we can have multiple points in a transaction. So in a transaction, in one serial transaction, we can have multiple such points, which we can mark as a save point. Okay, so save point is such a point in the transaction when you can roll the transaction back to a certain point without rolling back the entire transaction. So let's say I have 5 or 6 steps in a transaction. Now I only want to roll back till the third step. So before the third step, if I have a save point, then I can say that, okay, roll back to this save point, not the entire transaction, because not always it is required to roll back an entire transaction. Just parts of it is rolled back. Okay. So syntax for save point is save point name. Now this command serves only in the creation of a save point among all the transactional statements. Anyways, all these things are not required. See this example you see. Save point SP1. SP1 is the name of the save point. So this is created. This is creating a save point. Then I perform some delete operation in customer table. Okay, where ID is 1. So one row is deleted. Now after this delete operation, I created one more save point SP2. Then some other delete operation is done where ID is 2. One more row is deleted. Another save point is created SP3. Then one more row is deleted. Okay, this is the way the transaction is happening. So this is the actual commands in SQL for that. So save point SP1 delete from customers where ID 1. So 3 delete operations you made and 3 save points you made. Now, after this is done, if you say roll back to SP2, that is this point, okay, then what will happen? These 2 delete operations will be undone, but this one will prevail. See, initially this was the table, right? So if I delete ID1, which one is deleted? This row. I deleted ID2, this one is deleted, ID3, this one is deleted. Okay, but none of these changes are committed yet. And I have created 3 save points. After this, if I say roll back to SP2, that means this step. So if I roll back to SP2, then everything from the end till SP2, all of that has to be rolled back. That means these 2 delete commands I will roll back or undo. So that's why in the final table, after the rollback is done till SP2, see only rows 2 and 3 are recovered. Row 1 is still deleted, right? Because I didn't roll back till SP1. If I rolled back till SP1, then this will also be present. Now, if I roll back till SP3, then which row will not be there?
1 and 2.
2.
So 1 and 2 will not be there. Only 3 will be recovered. This is the concept of save point. Basically, it is just a type of rollback. Instead of rolling back the entire transaction, I can roll back to whatever point I choose. So for that, you have to create the save points at particular places where you want. Now, next is concurrency control.
Ma'am,
If there is any commit in between during these save points, does that have any effect on what is
Yeah, if
recoverability?
you commit, then you cannot roll back. Once commit is issued to a transaction, no rollback happens.
So after like save point two or something like that, if there is a commit, it will only roll back till.
So it then you cannot roll back. Once there is a commit issued, if after save point 2 and this delete id 2, if there is a commit, then there is no way you can roll back to save point sp2.
Okay.
So will it
Save,
delete
save
the?
points also will get deleted.
Will it
Yeah, see,
delete?
first thing is that in a transaction you cannot issue commit everywhere, right? There is only one commit statement which comes when the transaction is done, it is completed. So once that commit is issued, then there is no rolling back. That is why we saw
Um,
this example. See
so,
here.
ma'am, once the commit is issued, all this everything is saved, including then there won't be any more save points, ma'am.
No, after that there is no need for save point once commit is issued.
Okay. If there is a system failure, then we'll go back to the latest save point, ma'am.
Latest save point or whatever save point you want to go to. If you have
Okay.
2 3 save points, you can choose any. See here that like we did this example, after this commit is issued,
Sorry, ma'am. So
right?
what is the difference between save point and commit, ma'am?
Save point is just a type of rollback command. So instead of rolling back the entire transaction, you can issue save point till the point where you want to roll back. So instead of rolling back the entire transaction, if you just want to roll back the last 3 steps, so before the after you issue, wait,
No, my question is both the commit and save point
commit
is
and
help.
save point are different things. Commit means that you are committing changes. Whatever
Okay.
changes you made, you are committing them permanently to the database. Save
In
point
case
is
of
about rollback.
system failure, then the save point will work or not, ma'am?
Yeah, it will work. If you haven't committed yet, then you can roll back to whichever save point you want.
Yeah. So that means save point is also a way of saving data, is it, ma'am?
I won't say saving, but save point is basically rolling back till a particular point. Like it's
Okay.
kind of like a checkpoint. Okay,
Okay.
that till this point I will have here I will issue a checkpoint and I can roll back till this place. See, in this example, like we saw, this rollback, it happened directly after the delete, right? If there is a commit here, then can I do the rollback? No. It happens directly after the delete. That's why no commit is issued here. Save point is just instead of rolling back, I am writing a save point so that I can have multiple rollback points. I'll take one example. There are multiple problems on save point if you check the PYQs. But first, let's
Yeah, in
complete this.
Windows, we have this system restore kind of a thing. Is it comparable with this?
That restores the entire system, right?
No, no. We can select a date now. We can create a directory with the backup dates, and when a system crashes, we can restore it to the previous some
Yeah, yeah,
day.
yeah. Yeah, you can compare it to that. Yes. See, save point actually gives you more flexibility for rollback because not always we need to roll back an entire transaction. So you can roll back till the point that you need. Now, concurrency control. This is what that basically what is the most desirable type of transaction or schedule? A schedule that is serial, right? We always want a concurrent schedule to be equivalent to a serial schedule, right? But serial schedules are why do we have concurrent schedules? Why, if serial schedules are so good, that is, there are no problems in serial schedules like this conflict operations, then why do we do concurrent schedules? What is the trade off? If I have three
I'm sorry,
transactions,
ma'am. Could you please repeat the question one more time?
yeah, I asked that we all know that serial schedules are the best type of schedules. There are no conflicts there. Then why do we have concurrent schedules? What is the trade off?
Time.
Time. And it is like the cost also increases. Now, if your processor, like your processing power is very high, but you are just using serial schedules, that is, you are just using the processor to perform one transaction at a time, but your processor has a higher processing power. So you are not utilizing the power and you are using a lot more time than needed. So that's why we have concurrent schedules, but whenever concurrent transactions, but whenever we have concurrency, there is a chance for all these things to happen, right? This conflict operations, all of this inconsistent state. Now, what we need is we want the stability of serial schedules and the speed of concurrent schedules, but we cannot achieve both of them 100%. So we do concurrency control. That means we, what can I say? Oh, basically, we try to get as much concurrency as we can while still maintaining the integrity of that serial schedule. So how can I perform this concurrency control? The database must provide a mechanism that will ensure that all possible schedules are both conflict serializable, recoverable, and preferably cascadeless. So these are all three things that we want. Now, a policy in which only one transaction can execute at a time generates serial schedules. Okay, so if there is a policy in which only one transaction can execute at a time, that is serial schedule. But it provides poor degree of concurrency. That means two transactions are not happening at once, or more than one transactions are not happening at once. Concurrency control schemes trade off between the amount of concurrency they allow and the amount of overhead they incur. That means I am allowing concurrency, that means more than one transaction to happen at a time till a certain level, and I am also making sure that the overhead is not too much. The cost is not too much. So testing a schedule for serializability after it has executed is not desirable, right? We want all of these things to be pre-decided, that it is going to be serializable, it is going to be recoverable, preferably cascadeless. All of these things will make sure before the transaction runs. Now, what is our goal? Our goal is to develop a concurrency control protocol that will assure serializability. So one way to ensure this is what? One way of this concurrency control is what? To ensure isolation is to require that data items can be accessed in a mutually exclusive manner. Now, why does this happen? Why does this conflict happen? Because two transactions are accessing a single data item simultaneously, right? So if I perform a write operation on a data item in two different transactions at the same time, that will lead to an inconsistent state, right? That will lead to a conflict, write conflict. So how can I make sure that this doesn't happen? If I can make sure that that variable can only be mutually accessed, can only be accessed in a mutually exclusive manner. Mutually exclusive means if transaction T1 is accessing variable A, transaction T2 cannot access it. And if T2 is accessing the variable, T1 cannot access it at the same time. That is mutual exclusion. So if I can ensure mutual exclusion, then I can say that, okay, isolation will be maintained. That is, transactions will be independent of one another. Okay. So should a transaction hold a lock on the whole database? So if a transaction holds a lock on all the variables, then that will give rise to serial schedules, right? Then that is, this transaction will first complete all of its operation, then the next transaction will start. So that is very poor performance. Like we said, I'm not utilizing my processing power. Now, the most common method used to implement locking requirement is to allow a transaction to access a data item only if it is currently holding a lock on that item. So now we will start lock-based protocol. See, the main idea is that if there is a data item A, okay, data item A, transactions T1 and T2 are there. T1 is also trying to access A. T2 is also trying to access A. Now, whoever T1 or T2, whoever first issues a lock on the variable A, they will be able to work on that variable, and the other transaction cannot access it. So till what time this will happen? Until that lock is unlocked. So if T1 issues a lock on variable A, then T1 can only access A, T2 cannot. Then T1 can perform whatever operations it needs to perform on A, and then it can unlock. Then only T2 can lock variable A. So this leads to mutual exclusion. Now we'll see how that is implemented. See, first we are doing just lock-based protocol. Okay, two-phase locking is different. So a lock is what? It is a mechanism to control concurrent access to data item. That is, two transactions cannot access the same data item at the same time. Now data items can be locked into two modes. One is exclusive lock, one is shared lock. I'm audible, right? You're very quiet.
Yeah, ma'am.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay. See, there are two different types of locks. Okay, one is a shared lock, one is an exclusive lock. So which is the more rigorous one is the exclusive one. So shared lock does what? If a data item, if a shared lock is issued on a data item by a particular transaction. Let's say T1 is issuing a shared lock on data item A. Then T1 can only read the value of that data item A. It cannot write. If transaction T1 issues an exclusive lock on data item A, then it can read A as well as write A. Both can be done. So exclusive lock will be mentioned by X lock. This is how it will be denoted. And S lock means shared lock. Now a transaction can unlock a data item Q by the unlock Q instruction. So first, if I say X lock A, this means I issued an exclusive lock on data item A. Then let's say I perform read A, write A, whatever I need to do. Then I did unlock A. So at this point, let's say this is transaction T1, it has unlocked the variable A. After this, transaction T2 can issue, let's say, a shared lock on A or an exclusive lock, whatever it wants, but not before this unlock happens. Now a transaction can unlock a data item Q by the unlock Q instruction. Lock requests are made to the concurrency control manager. That is, these locks that we are issuing. So you have to first make a request to the concurrency control manager. If that request is granted, then only you can issue the lock. Now this one is very important. This is a lock compatibility matrix. Okay, so shared and exclusive locks have some differences. So on a data item A, if a shared lock is issued by transaction T1, then transaction T2 can also issue a shared lock on data item A at the same time. Why? Because they are just reading the data. After you issue a shared lock on a data item, you can only read it, you cannot write it. So we all know that read is not a conflict operation, right? If two transactions perform reads on the same variable, is it a conflict?
No, no.
No. So same thing happens in shared lock. If both transactions are issuing shared lock on a particular variable, then that is not a problem. That can happen. So let's say T1 and T2 are two transactions. So T1 said, I want to issue an S lock on A. This is granted. Then let's say it is performing a read on A. At this point, T2 is also trying to get an S lock on A. So this request will also be granted at this point, even though A is not unlocked by T1 yet. So that is why this is called a shared lock. That is, two or more transactions can share a lock on a variable if they just want to make a read operation. But if I issue an exclusive lock, then this cannot happen. So basically what is possible, that is why this matrix is given here. See this one, look at this one. Unlock is not needed. So if a shared lock is issued, then another transaction can also issue a shared lock. So shared is yes. Now if T1 issues a shared lock on A and T2 wants to issue an exclusive lock on A before this shared lock is unlocked, that is not possible. Okay. Another thing, exclusive lock. If exclusive lock is issued on A by transaction T1 and T2 is trying to issue a shared lock, that is also not possible. And if exclusive lock is obtained on item A by transaction T1 and T2 is also trying to get an exclusive lock on A, then that will also not be possible. So only one thing is possible, that shared locks can happen together. On a same data item, T1 and T2 can issue shared locks at the same time. But shared and exclusive lock cannot happen together. Exclusive and shared lock cannot happen together. Exclusive lock definitely cannot happen together. Okay. So whenever exclusive is involved, it cannot happen until the variable is unlocked. So Let
Ma'am,
me ask.
if in T1, if there is an exclusive lock on A and after it is unlocked, then also can't T2
Yeah,
use that?
after unlock you can do anything you want, but
Okay, so
during
this
the lock
table
is
is
issued.
okay. So this table is during when there is no unlocking.
Yeah, this table is during when there is no unlock.
Okay, ma'am.
So if see here T1 issued S lock. Now before unlock also T2 can issue an S lock. But if at this point instead of S lock T2 wanted to issue an X lock, this is not possible.
Yes, ma'am. Okay, ma'am.
Okay,
Got
on
it.
the same variable. On different variables you can.
It is
Now,
same like read and write part.
yeah, same thing. Now let's take a small example. So this is a serial schedule, okay. So A and B are two accounts that are accessed by transactions T1 and T2. Transaction T1 transfers $50 from account B to account A. Okay, and transaction T2 displays the total amount of money in accounts A and B, that is the sum A plus B. Just give me 1 second, I'll be back. Yeah, okay. See. So transaction T1 transfers $50 from B to A. Right. I'm audible?
Yes, ma'am.
Yes, ma'am.
Okay. So first of all, if I want to transfer 50, that means I have to change the value of B, right? So if B has 100 initially and I want to transfer 50, so B has to be rewritten, right? So B will be B minus 50. So this write B has to occur. That means what kind of log do I need?
Exclusive lock.
Right. So if I take shared log, I can only read, cannot perform any changes. So I need an exclusive lock. So see, transaction T1 first issues an exclusive lock on B, lock XB. This is exclusive. Then it performs a read operation, then it changes the value, performs a write operation. Then B is unlocked. Fine. Now it is saying transaction T2 displays the total amount of money in accounts A and B. Okay. So T1 hasn't finished yet. So this is the serial schedule. So first T1 has to finish. So after this, T1 issues exclusive lock on variable A. Then it reads A, adds 50 to A because it is transferring 50 to from B to A. Na? So that 50 has to be added to A's account also. That is happening here. Then write A, then unlock A. Then T2. So T2 has to do what? It has to just display the total amount of money in A and B. That is A plus B I have to do. So for A plus B, do I need to write anything
No.
or make any changes? So just issuing, I just need to read A and B's value, right? So just issuing a shared lock will do. So I will first do shared lock on A, read the value of A, then unlock A. Then shared lock on B, read the value of B, unlock B. Then display A plus B. So these two serial schedules, these locks are clear for everyone.
Yeah, ma'am.
Yes,
Now
ma'am.
when I want to do this concurrency,
Ma'am, excuse me, ma'am, can you explain once again this?
see first in T1 what I want to do is transfer $50 from B to A. That means I have to take out 50 from B, give 50 to A. So I have to change the values of A and B both. That means I have to perform write operations. So if I want to write operations, what kind of log do I need? Shared or exclusive?
Sure.
Shared does only read. Exclusive will give
Exclusive.
you access for read and write both. So we want exclusive log. So first I have to take out $50 from B's account. So first issue an exclusive log on B. Then read the value of B, current value of B, subtract 50, write the new value. then unlock B because you are done with this B variable. Next, again, issue an exclusive lock on A, read the current value, add that 50 back to A, write the new value, unlock A. So T1 is done. T2 only has to show the current sum of A and B. So if I want to show the current sum, I just need to read what is stored in A, what is stored in B. No write is required. So what kind of lock do I need? Shared lock. Exclusive, even with exclusive you can do it, but it is not required. Shared is enough. So just issue a shared lock on A, read the value of A, unlock A. Issue a shared lock on B, read the value of B, unlock B. Then display A plus B. Okay, clear? This is happening serially. First T1 occurs, then T2 occurs. Okay. Now, if I want to do this concurrently. Okay, so this is the concurrent schedule that I'll. Is it visible properly?
Yes.
So I am now doing this concurrently. So first T3, we are calling this T3 and T4 now. So first T3 is asking concurrency control manager to issue an exclusive lock on B. So this request is granted. Okay. So then after the lock is issued, it does a read on B, then changes the value of B from B to B minus 50. Yeah, from B then we take out 50. Then write the new value of B. Now after this is done, I can unlock B, right? Because I'm done with B now. At this point, T4 now wants to issue a shared lock on A. So it sends a request to concurrency control manager that I want a shared lock on A. That request is granted. Because why this request is granted is because there are no locks on A at this point, which are exclusive. So tell me one thing, after this unlock B, if I here had a lock XA, then could I issue this shared lock on A in T4?
No.
No, ma'am.
No. But if I had a shared lock on A here, then could I do this?
Yes.
Yes, ma'am.
This is
Yes.
possible, right? So this shared lock is issued on A, then it reads the value of A, again asks for shared lock on B, reads the value of B, displays A plus B. Now, at this point, you have to tell me if this is correct. Okay. At this point, what was the value of, let's say, A started with 0, B started with 50. Okay. So after this part is done. What is the value of B right now?
0.
And what is the value of A?
0.
Both are 0. So when it reads these two items, it will read 0 in both. And then display A plus B, this will also be 0. Because this part of the schedule, this part of the transaction happens after this display. So this is wrong, but I'm just showing you how the concurrency is working. Then it is trying to issue an exclusive lock on A here. This will be granted or not? It will be granted, right? Because this unlock operation happened here. If this unlock was not here, that is, this shared lock was issued, but it was never unlocked, then can I issue exclusive lock on A here?
No.
No, ma'am.
But since unlock happened, so I can issue that. Then you do read A, add 50, write A, unlock. Okay, this is just an example. Now see what, this is how locks are issued and all, but something called a deadlock can occur because of these lockings. What is a deadlock? Now given T3 and T4, consider schedule 2. Okay, this is the schedule 2. So since T3, okay, since T3 is holding an exclusive lock on B and T4 is requesting a shared lock on B. Look at T3 and T4. So T3 does what? This is the serial part. Okay. So first T3 is issuing exclusive lock on B, reading B, all of these things that happened earlier. But what is the change here? After it issued exclusive lock on B, it did the read B, then subtracted 50, write B. Then it issued exclusive lock on A, read A, add 50, write A. But all the unlocking is happening at the end, right? That's fine. Then T4 does what? Shared lock on A, read A, shared lock on B, read B, display A plus B, then unlock AB. Now, in this schedule 2 look, first exclusive lock is issued on T3, then read B, then B equals to B minus 50, write B. No unlock has happened yet. Okay. Then a shared lock. So this shared lock on A can be issued, right? Because these are different variables.
Yes, yes, ma'am.
Then read A. Then can I issue a shared lock on B here?
No.
No.
This is not possible. This is wrong. So it is asking for a shared lock on B. But it cannot get it because B has not been unlocked by T3 yet. But also the next step, T3 is asking for an exclusive lock on A. But I cannot do this either because this A has not been unlocked. So this is a deadlock situation where you cannot proceed with the any of the transactions because T3 is asking for something that T4 has not unlocked, and T4 is asking for something that T3 has not unlocked. So unless any of them unlocks, I cannot move forward. So this situation is a deadlock. In case of deadlock, what you have to do is you have to roll back any of the two transactions. There is no other way to get out of it. Okay. So when a deadlock occurs, the system must roll back one of the two transactions. Now, once a transaction has been rolled back, once a transaction has been rolled back, the data items that were logged by that transactions are unlocked. So if I roll back T2 here, one second. So in this one, this is a deadlock situation. So if I decide to roll back T4, then which locks will be unlocked? If I roll back T4, what will be unlocked?
Lock B and A.
Lock A will be unlocked. Only lock A was issued. Lock B asked for a lock, but it could not be granted because this lock was already on lock B and it has not been unlocked. Similarly, if I roll back T3, what lock will be unlocked?
Lock B.
Lock B will be unlocked. So in case of deadlock, you just have to roll back one of the transactions so that one of the locks are unlocked. Okay. So when rollback occurs, what happens is that all of the data items on which that transaction has a lock will be unlocked. So this is deadlock. Now this is the most important and definitely question will come from here. Okay, two-phase locking. So why this is called two-phase? See, the locks are same. Okay, shared and exclusive only. Why this is a two-phase locking is because here the lock and unlock, these two happen in two different phases. So we have two phases. First is the growing phase. Growing phase is when you issue all the locks. Okay. So when you issue the lock, it is growing phase. When you unlock, it is shrinking phase. But the catch is that once growing phase ends and shrinking phase begins, after that you cannot issue any more new locks. That is, once you have started unlocking, you cannot ask for any new locks. Okay. So this means that all the locks that you need has to be issued at in the beginning only. Because once unlock is issued on any of the locks, after that you cannot issue any new lock on any other variable. So in growing phase, what does the transaction do? It obtains all the locks and it does not release any of the locks. In shrinking phase, it releases all the locks, but it does not obtain any new lock. So first growing phase will happen, then shrinking phase will happen. Now, let's take an example. Okay, one more thing is that growing phase, see, three things can happen in growing phase. You can either issue a shared lock, you can issue an exclusive lock, or if you have a shared lock on some variable, you can upgrade it to an exclusive lock. These three things you can do in growing phase. Now, in the second phase or the shrinking phase, you can either release a shared lock, you can release an exclusive lock, or you can change a variable that had an exclusive lock to a shared lock. That is, you can downgrade the lock. Obviously, exclusive is an upgrade. Exclusive lock allows more operations, so it is an upgrade. So if you already have exclusive lock on some variable, you can downgrade that to a shared lock in shrinking phase. So these are the operations that happens in growing and shrinking phase. Okay. This is an example of a deadlock again, I think. So two-phase locking does not ensure freedom from deadlocks. So we saw that without two-phase locking also deadlocks can happen, but with two-phase locking also deadlocks are there. It can happen. Okay. We cannot eliminate them. So see this example. This is this first we have the serial version. Okay. So T3 and T4 same serial schedule, but this is following two-phase locking protocol now. Okay. So first locks are issued. So tell me up to which is the growing phase? Up to which statement do we have growing phase in T3?
Till the
Till what?
Right, right A.
Till right. That is till the first unlock. So all of this is in growing phase. This is the shrinking phase. Okay. Here also, all of this is growing phase. This is shrinking phase. Now when I write it concurrently in this form, again you see deadlock is happening. So we issued exclusive lock on B, read B, B equals to B minus 50, write B. But B has not been unlocked yet. Again, lock on shared lock on A, read A. Then it is asking for lock on B, shared lock. But since B is already exclusively locked by T3, shared lock cannot happen until B is unlocked. But T3 also needs to issue exclusive lock on A, which has already been taken by T4. It has already issued a shared lock on A, and this cannot be issued until T4 unlocks A. So T4 cannot unlock A because this is what two-phase locking. So you cannot have an unlock before this. So can you tell me something? If after this read A, I issue unlock A. This is two-phase locking, remember. After that, can I issue lock SB?
No, ma'am.
Because as soon as I do unlock, the shrinking phase starts. After that, no new locks can be issued. So this is also still a deadlock. Okay, so that means that two-phase locking cannot ensure that there will be no deadlocks. What is starvation? So in addition to deadlock, there is a possibility called starvation. Starvation usually means what? That some transaction is waiting for a variable for a long time, but it is not getting any access to that. So starvation occurs if the concurrency control manager is badly designed. That means a transaction may be waiting for an exclusive lock on an item, while a number of other transactions are getting shared locks on it. So let's say T1, T2, T3, and T4. There are 4 transactions. Now T1, let's say T2 first asked for a shared lock on A. Then T1 asked for an exclusive lock on A. Can this happen?
No, ma'am.
But then T3 asked for a shared lock on A. This can happen.
Ma'am, is the sequence matter? The T2, T1, T3?
Yeah, sequence matters.
Then not possible.
See, no one has unlocked yet. So T2 has a shared lock on A. After that, T1 is asking for exclusive lock, but it cannot be granted. But if T3 is asking for another shared lock, can this be granted?
Yes.
If T4 is also asking for another shared lock on A, will this be granted?
Yes.
So that means even though T1 asked for this exclusive lock before T3 and T4, T3 and T4 are getting access to A, but T1 is not. So T1 is getting starved. This is starvation. Okay, so starvation occurs when a transaction is asking for an exclusive lock on an item, it is not getting access to that, but a sequence of other transactions are getting uh, shared locks on that same item. The same
Ma'am,
transaction is repeatedly rolled back.
ma'am,
Hmm.
Since the T3 and T4 asking for that S lock, shared lock for the same A, and that's why if T2 is not even unlocking it, they can share.
Yeah. See, shared lock can happen together, right? Shared is fine. See, remember that matrix that if
Yes,
shared
yes,
lock is issued, other transactions can issue shared locks.
yes,
But
ma'am.
for
Yes,
exclusive lock, it will not happen.
yes, ma'am.
So T1
Safe.
will get starved, but T3 and T4 will get access.
Oh, yes. Okay, got it, ma'am.
Hmm. So this is starvation. It is also known as live lock. Okay. Now there are two other types of two-phase locking also. We did normal two-phase locking. There is another thing called strict two-phase locking. So strict and rigorous are not in our syllabus. Just the definition you can know. Strict two-phase locking. So in normal two-phase locking, what is the rule? That all the locks have to be acquired in the beginning, in the growing phase, and after unlock has been issued, no more new locks can be issued. Right? That is once shrinking phase starts, no more new locks. Now, strict two-phase is a bit more stricter on this. It says that a transaction must hold all its exclusive locks till it commits or aborts. Okay, that means till the end, it must hold all the exclusive locks. Rigorous two-phase says what? That all locks are held till commit or abort. Because until commit or abort happens, no unlock operation will be there. So why strict two-phase is a bit more strict? Because it is holding only exclusive locks till commit or abort. And rigorous is even stricter because it is holding all kinds of locks, shared or exclusive, till commit or abort happens. Okay. So these two actually can give you a much better concurrency controlled schedule. Okay, but we are not going to discuss this. We'll just do normal two-phase locking. So let's do this one question. If you can solve this, then all the questions present will be easy for you to solve.
Ma'am, one doubt. What is the advantage of this two-phase locking if it is not going to avoid deadlocks or, I mean, it's not going
It will
to.
give you good concurrency management. That means it will not give rise to that conflict that two
Okay,
transactions are trying to access the variable at the same time. It is giving you mutual exclusion. Okay.
okay,
So locking, the point of locking is to achieve mutual exclusion. That means when one transaction is working on a variable, another transaction cannot work on the same variable. So
okay.
this is one question which includes all the types of question that can come from this two-phase locking. So mainly they will ask you whether it is conflict serializable or view serializable and whether it is two-phase lockable. Okay, this is the type of question you will get. So just solving this one question is enough. The S1 is doing what? S1 is a schedule, S2 is a schedule. So we have to check everything. First option is asking is S1 conflict serializable. Let's solve this. We have to draw the schedule. So how many transactions are there in S1?
3.
3. So let's draw this T1, T2, T3. So first we have write on A on transaction T3. So this is W3A will be here. Then R2A. Then W2A. W3B. W3C. And W1C. Okay. Now you tell me, is there a conflict from T1 to T2?
Yes. No, ma'am.
T1 to T2 there is a conflict.
No, ma'am.
No, ma'am.
T1 to T3?
No.
No, ma'am.
Because why there cannot be a conflict between T1 to any of the transaction is because we don't look from bottom to top. We look from top to bottom. That means we don't see for conflicts like this. We see for conflicts like this. Down arrow always. Okay, because we don't go back. This W2 has occurred before this W1. So
Ma'am, can you explain again it again?
see T1, if this W1C happened here, okay, then I can say that there is a conflict, right? Between T1 to T2. I'm sorry, T1 to T3.
Yes.
Okay, because this arrow is going like this. But
Yes.
since this W1C is happening after the W3C, this is the actual transaction, right? So this W1C is happening after the W3C. So the conflict will not go like this, W1C to W3C. This is wrong.
Okay.
Conflict will go from W3C to W1C. Okay. So always
Okay.
we take downward arrows, not upward arrows.
Okay. Got it.
Yeah. So what are the conflicts? So one is from T3 to T1 we have one conflict. Then from T2 to T3 do we have a conflict?
No, ma'am.
No, ma'am.
From T3 to T2?
Yes,
We
ma'am.
have T3 to T1, we have, ma'am.
T3 to T1 we have one, this C, right C. And T3 to T2 we also have on right A. So apart from these two, are there any more conflicts?
Ma'am, there was one more conflict, no? WA and RA in T3 and T2.
This one you're saying. Yeah, I am not writing this because once we find an edge, we don't need to see for other conflicts. Okay. Because once we find one conflict from T3 to T2, that means there will be an edge from T3 to T2. So if there are even more,
Okay,
you
ma'am.
don't need to mention. Okay. So this is it. Now draw the precedence graph. So it will have three nodes T1, T2, T3. So what are the edges? Tell me what are the edges?
T3 to T1.
T3 to T2.
T3 to T1 ones and T3 to T2 ones.
T3 to T2.
Nothing else. So is this conflict serializable?
Yes, ma'am.
Yes.
There
Yes,
are
ma'am.
no cycles, right? So S1 is conflict serializable is true, correct? Next is asking is S1 two-phase lockable? Let's see. So we have to now draw the same schedule with locks. So T1, T2, T3. Okay, so what is the first operation? Write on A in transaction 3. So if I want to perform write, then what kind of lock do I need to issue?
Exclusive.
Exclusive.
So X lock on A in transaction T3. Now can I perform write? Yes. So W3A. So at this point, will I unlock A in T3?
No.
Why?
We will have to, right? Because otherwise it
So
cannot be read.
if I unlock A here, then can I issue more locks on W3 later on T3 later on? Because I still have
Okay.
an operation of write on B.
No, no,
This
no.
will violate two-phase locking, right? Because shrinking
Correct, correct,
space start here.
correct.
So I won't unlock. So I will do what? I will next issue the next lock that I need.
Ma'am, could you please explain again?
So if I unlock A here, after this, can I issue another lock on B, another exclusive lock? Because there is an operation W3B. Is this possible? In two-phase locking, is this possible? Once an unlock statement is issued, after that you cannot issue any more locks. Because here shrinking phase is starting. So this is wrong. So I cannot unlock A right now.
Okay, ma'am.
So what will I do? Check that in transaction T3, what other locks will I need in future? I will need a lock on B and I will also need a lock on C. Correct? So let's issue those locks. So X lock on B and X lock on C. Up to this I can do. After this, can I do unlock A?
Yes, ma'am.
Okay. Now I performed unlock A. Next operation is read on A on transaction T2. So if I want to perform only read, what kind of lock do I need?
Share.
So
Sure.
now unlock has been done. So I can issue a shared lock.
Yes.
Shared lock on A. Done. Then I can do read on A. Then transaction 2 wants to do a write on A. So I can upgrade this shared lock to an exclusive lock
Yes.
and then do the write. Next operation is W3B. So B is still locked by transaction T3, right? B was not unlocked. So I can perform this operation W3B. Okay. Then W3C. C also, I also have a lock on C here. So I can perform W3C. So after this is done, then can I unlock
Yes.
B and C? So let's
Yes.
unlock B, unlock C. Next I have W1C. So at this point C is unlocked. So I can issue an exclusive lock on C in transaction T1 and then perform my W1C and then I can issue an unlock statement. Okay. So is this two-phase lockable? How will you check? Check all the three transactions whether the growing phase and shrinking phase are correct. So in T1,
Ma'am,
yeah,
T2 when do we unlock A, ma'am?
T2, yeah, you can unlock A here, no problem. Because no one is issuing A after this. That's why I didn't write it. But yeah, T2 can unlock A after it is done with the write. So first check in T1. Growing phase, shrinking phase is correct, right? Because after the shrinking phase started here, no more locks are issued. So T1 is following two-phase locking, correct? Yes or no? In T1, what happened? I issued an exclusive lock on C. Then I did the write operation on C. Then I did unlock on C. So growing phase and shrinking phase are correct, right? After this unlock on C,
Yes.
did I issue any more new locks in T1?
No.
So T1 is following two-phase locking protocol.
Yes.
Now check for T2. In T2, what is the growing phase? Till this. This is growing phase. Then this unlock is the shrinking phase. After this unlock, is there any more new locks?
No, ma'am.
So T2 follows two-phase locking. Now check in T3. Till this is the growing phase. After this unlock, this is the shrinking phase. So in shrinking phase, do you see any more new locks?
No.
So T3 is also following two-phase locking. So can I say that schedule S1 is two-phase lockable?
Yes.
So even if one of the transaction fails two-phase locking, then the schedule is not two-phase lockable. So check for all transactions.
Ma'am, how here T3 is a two-phase lockable?
So you issued all the locks till here. This is the growing phase. First unlock statement is here. That means this marks the beginning of shrinking phase. So after this unlock, are there any new lock statements?
No, ma'am.
That means this shrinking phase is correct. If I
Yes,
issued
ma'am.
any more new locks, then shrinking phase will be violated. But these are both correct, growing and shrinking. So this is in two-phase lockable. So S1 is two-phase lockable. Similarly, you have to check for S2 now. Should I erase this? Everyone got this?
Yes, ma'am.
Okay.
Yes.
Okay, now next is we have to check whether S2 is conflict serializable or not. So let's check S2. How many transactions are there again? 3.
3.
So let's write that. So T1, T2, T3. First we have W1A, then W3A, W3C, W2A, W1B, See, these are all blind writes. Then W3B. Now tell me, T1 to T2, is there any conflict?
Yes, ma'am.
Right. T1 to T3?
Yes.
Yes, ma'am.
Okay, again right. This is also conflict. Now T2 to T3, is there a conflict?
No, ma'am.
No. Okay. One second. T3 to T2?
Yes, ma'am.
This. Any other conflicts? Let's draw the precedence graph. T1, T2, T3. What are the edges?
T1 to T3,
T1 to T3.
T3 to T2.
Will I have any edge from T1 to T2?
Yes, ma'am.
Ma'am, I have a question on that. So, W1A, so should we consider only the immediate write on the T3, or should we also consider
Any
write?
write operations that happens after this write of A, any
Okay.
write that happens after this write of A on the same variable A in T2 or T3 will cause a conflict.
Okay. Thank you.
Okay. So T1 to T2 there is a conflict, T1 to T3 there is a conflict. Also T3 to T2 there is a conflict. No more conflicts. So is this conflict serializable?
Yes, ma'am.
Yes, ma'am.
Yes, there are no cycles. Okay. So this is conflict serializable. Fine. So option C is also correct. Now we have to check for locking. So T1, T2, T3. So first, what is the write operation? Write on A in transaction T1. That means what kind of lock?
Exclusive.
Exclusive.
So X lock on A. Now let's see what other locks will I need in transaction 1.
Lock on B.
So that is for read or write.
Uh,
Right.
right.
That
Exclusive.
means what kind? Exclusive. So X lock on B. Let's issue both. Now if I want to perform write on A, I can perform. Okay. Next is what? Write on A in transaction 3. So let's first unlock A here. I can do this. Okay. So now here shrinking phase starts. So after I unlock, now I can issue the same exclusive lock in T3. This is fine. Right?
Yes.
Now, after this exclusive lock on T3, check in T3 what other locks will I need in future.
Exclusive lock on C.
So let's issue that also. So this is the best way of solving these questions. First issue all the locks you need in a transaction. Okay. Now, you can write W3A. Okay. I can also write W3C. Okay. So this is done. This is done. This is also done. Next, I need a write A in transaction 2. So I have to unlock A here. This marks shrinking phase. After this, no new locks.
Ma'am, there will be an exclusive lock on B also for T3.
Yeah, there will be. Okay, but okay, fine. If you want to issue that lock here, exclusive lock on B.
Yeah.
So can I issue this exclusive lock because I haven't unlocked B here in T1? I already issued exclusive lock on B in T1.
Okay. No.
But T1's write has not yet been performed. So I haven't unlocked that. Right.
Yeah.
So no, I cannot issue that lock in T3. So now let's perform this write on T2. So A has been unlocked, so I can issue exclusive lock on A here, right? Then I can do WT A. Now I need to do what? W1B. Okay. See if I do W1B here and then unlock B. After this, can I issue exclusive lock on B here?
Yes.
Yes, ma'am.
No, we cannot. Because shrinking phase started once you unlocked A. After that, you cannot issue any new locks. So T3 is violating two-phase lockable. That means this whole schedule is not two-phase lockable.
Right.
Understood? Why this happened? Because I couldn't issue this lock on B in T3 during the growing phase. Why? Because T1 had already issued it and didn't unlock because W1B was pending. So this is not a two-phase lockable schedule. So last one is wrong. Is this question clear to everyone?
Yes, ma'am.
Yes.
Any doubt? Anybody? Okay, good. So this is the highest difficulty type of question that you will get from two-phase locking. Okay, so as long as you are comfortable with knowing when what is growing phase, what is shrinking phase, these things if you can do, you can easily solve the questions. Okay. Also do one thing, since your deadline is today and we don't have time to practice more, so just check out the last term's end term discussion. Okay. So in end term revision session, I think we discussed more problems on two-phase locking.
Ma'am, this S2 is not two-phase lockable because of the last write
Because
on
of
B,
this
right?
three, right, because of this T3 transaction, because I want an exclusive lock on B, but shrinking phase already started.
But then if we had issued the exclusive lock on B before the
How could I
unlock of,
issue? Because T1 had already issued exclusive lock on B here, and it
but
had
if,
not unlocked
oh,
because this W1B was pending.
okay, ma'am.
Okay. Okay. So next is deadlock prevention. Now we have timestamp protocol. Okay, this is the last topic. So deadlock prevention method is what we saw what deadlock is, and it cannot be prevented even by two-phase locking. So what we can do is something called time transaction timestamp. Now, if you check out 10.5, there are a lot of things in it, but mainly what is important in 10.5 is wait and die and wound wait scheme. Okay, so these two schemes you just need to properly know. Others you can just go through once. So transaction timestamp is what? Timestamp is basically a unique identifier created by the database to identify the relative starting time of a transaction. Basically, we give a timestamp to the starting time of any transaction. So timestamping is a method of concurrency control in which each transaction is assigned a transaction timestamp. Okay, timestamp can be 1, 2, 3, 4, whatever you want. Now, these are the two different schemes. Okay, one is wait and die scheme, one is wound wait scheme. So following schemes use transaction timestamps for the sake of deadlock prevention. So in wait and die scheme, what happens? Older transaction may wait for younger one to release data item. Older transaction means transaction that has a smaller timestamp. So let's say I have two transactions, T1 and T2. T1 has a timestamp of 5, T2 has a timestamp of 10. So from this, which one is older transaction?
5.
T1,
T1.
T1 is older. Whichever has the smaller timestamp is the older transaction. Okay. So older transaction can wait for younger transaction to release data item. So T1 can wait for T2 if T1 wants some access to some data item which has already been locked by T2. So T1 can wait for T2 to unlock. Okay, this is in wait and die scheme, this is fine. But younger transaction will never wait for older ones. So if T1 has some data item that T2 wants, T2 cannot wait for T1 to unlock. T2 will roll back. So younger transaction will roll back instead of waiting. So basically, T2 will die. So rollback is equivalent to die here. So it is wait and die. Okay. So a transaction may die several times before acquiring needed data. So T2 will die until T1 has unlocked the data item that it needs. and it can place a lock on it. So basically what you need to know is, in wait and die scheme, older transaction will wait for younger transaction to release data item, but younger transaction will roll back or die. It cannot wait for older one. In wound wait scheme, what happens? Older transaction wounds, that is forces the rollback of younger transaction instead of waiting for it. So in wait and die scheme, older transactions was waiting for younger one to release the data item. In wound wait scheme, older transaction will force the younger transaction to perform a rollback. It will not wait, it will force the younger one to perform a rollback, but younger transaction will wait for older ones. So in T1 and T2, T2 is younger. So if T2 wants a data item that is issued by T1, T2 can wait for T1. Okay, in wound wait scheme. But if T1 wants something that is issued by T2, T1 will make T2 roll back. So when rollback happens, what do we know? All the logs that are issued in that transaction will be unlocked when rollback happens, right? So T1 will force T2 to roll back. So in wound wait scheme, there are fewer rollbacks than wait and die scheme. So these are the two main schemes. See, this is an example of wait and die scheme. So what happens here is, when transaction Tn requests a data item currently held by transaction Tk. So Tn is allowed to wait only if it has a timestamp smaller than that of Tk. That is, Tn is older than Tk. So wait and die scheme means who can wait? Older transaction can wait, right? And younger one will not wait, it will die or roll back. So transaction Tn requests a data item currently held by Tk. Tn is allowed to wait when Tn is the older one, that is, it has the smaller timestamp than that of Tk. Otherwise, Tn will die. Now, if a transaction requests to lock a resource or a data item which is already held with a conflicting lock by another transaction, that means, let's say Tk has a lock on data item A, an exclusive lock on data item A. Tn also wants an exclusive lock on data item A. So this is what a conflict, right? This cannot occur unless Tk unlocks that data item. So two things can happen at this point. One is that timestamp of Tn is less than timestamp of Tk. That means Tn is the older transaction, which means it can wait until Tk releases the lock. But if Tn is the younger transaction and Tk is the older transaction, then Tn has to die or roll back. It cannot wait. So Tn will be restarted later on with some random delay, but with the same timestamp. So timestamp will not change. Timestamp will remain the same whatever it was before, but it will be restarted at some random time once it is killed. Okay. So this scheme allows the older transaction to wait but kills the younger one. So suppose this type of sums can come. The transactions will be given to you and the timestamps will be given to you. Okay, so suppose transaction T5, T10 and T15 have timestamps 5, 10 and 15 respectively. If T5 requests a data item held by T10, okay. So if first tell me which is the oldest transaction here between these three?
T5.
T15.
T5.
Oldest will be the one with the smallest timestamp. So who has the
Okay.
smallest timestamp? T5?
T5. Yes.
So T5 is oldest. Then T10, then T15. So if T5 wants a data item which is held by T10, then T5 will wait or die?
Wait.
Wait, because it is older. Now if T15 requires a data item which is held by T10, will it wait or die?
Die.
Because T15 is younger than T10. So this is how it will work. Okay, so timestamps will be given to you, transactions will be given, and this type of question will be asked, that if T15 wants to access a data item that is held by T5, will it wait or die? These things will be asked. Okay. Wound wait scheme, what will happen? So if transaction Tn requires or requests a data item currently held by transaction Tk, Tn is allowed to wait only if it has a timestamp larger than that of Tk. Otherwise, Tk is killed or wounded by Tn. So here basically what happens is that the transaction that is younger, okay, the transaction that is see this one. If a transaction requests to lock a resource data item which is already held with a conflicting lock by another transaction, then two things can occur. So if Tn has a lesser timestamp than that of Tk, then Tn will force Tk to roll back. That is, older transaction, if it wants something that the younger transaction is already locked, then older one will force the younger one to roll back or to be killed. Okay. And Tk will be restarted later. That is, younger one will be restarted later on with some random delay but same timestamp. Or the second case can be that the younger transaction wants something that is held by the older transaction. In that case, younger transaction can wait until older transaction unlocks that variable. So it is just kind of the opposite of wait and die. In wait and die, what happens? The younger transaction cannot wait; it has to die. But in case of wound wait, younger transaction can wait. So this scheme allows the younger transaction requesting a lock to wait if the older transaction already holds a lock, but forces the younger one to be suspended if older one requests a lock. Okay. So here also same example, T5, T10 and T15 are three transactions with timestamps 5, 10, 15. So if transaction 5 requests a data item held by transaction 10, so which one is older?
5.
T5 is older. So what will happen?
Yeah, it will force the T10
to roll back.
roll back.
Right. That is wounded. We also call it that it will force T10 to be wounded or roll back. But if T15 requests a data item from T10, then T15 can wait because T15 is younger. Okay, so these are the two main schemes. Now deadlock detection is what? These are for deadlock prevention. Okay, deadlock detection, what happens? So deadlock detection can be described as a wait for graph. So there is a graph of transactions, just like we did in conflict serializability, that precedence graph. So there is one more graph called wait for graph. This graph is used for what? Deadlock detection, which consists of a so graph. If the graph is called G, it will have V and E. V is the set of vertices, E is the set of edges. Right. So if there is an edge from Ti to Tj, that will fall under the set of edges E. So if Ti to Tj there is an edge present, then there is a directed edge from Ti to Tj, implying that Ti is waiting for Tj to release the data item. So if there is an edge from Ti to Tj, it means that Ti is waiting for some data item that is already held by Tj. It is waiting for Tj to release it. So when Ti requests a data item currently being held by Tj, then the edge Ti to Tj is inserted in the wait for graph. This edge is removed only when Tj is no longer holding the data item. So the system is in a deadlock state if and only if there is a cycle in the wait for graph. So if the wait for graph looks like this, so Ti and T1 and T2 are two transactions. So T1 is wanting to access a data item that is held by T2. So there will be an edge from T1 to T2. But T2 is also waiting for a data item that is held by T1. So there will be an edge from T2 to T1. So this is a cycle. If a cycle is present, that means system is in deadlock. If no cycle, that means no deadlock. So these are two examples. This is a wait for graph. So tell me, this there is an edge from T18 to T20. This means
T18 is waiting for a data from T20.
so T20 has locked some data that T18 wants to access. Similarly, T19 is waiting for T18 to release some data. T17 is waiting for both T18 and T19 to release some data. But is there a cycle in this graph?
No, ma'am.
So that means there will be no deadlock in this schedule. But look at this schedule. Here T17 is waiting for data items from T18 and T19. T19 is waiting for T18 to release some data. T18 is waiting for T20 to release some data, and T20 is waiting for T19 to release some data. So T18, 19 and 20, they are in a cycle. Right? They are all waiting
Yes,
for
ma'am.
someone to release the data. So this cycle will give rise to what? A deadlock. So whenever there is a cycle in the wait for graph, there will be a deadlock. This is a deadlock detection method. Okay. Although these things will not be asked from you, like we won't ask you to draw the graph or anything. Just need to know what it represents. Okay. So this is pretty much your week 10. Everything is covered, I hope. So do you have any questions, whatever we discussed so far?
Yes, ma'am.
Yeah.
Yeah, in general, I mean, from a system failure perspective,
Hmm.
how will, I mean, either the database will be in a state where the commit has happened, right? I mean,
Hmm. Hmm.
and the buffers will have no data, whichever it processed, correct?
Yeah.
So, will there be a need for rollback? It is a implicit rollback, right? I mean, if the system crashes.
Hmm. Hmm. So
So,
main question is that you are saying that commit has been issued, right?
yeah.
So after commit is issued, no rolling back can be there.
Yeah, so there is no point of a rollback, a need for a rollback, right? I mean, where,
After commit, no, there is no need.
yeah, I'm trying to understand, like, so then when will the rollback is used?
Rollback will happen when that transaction has not been committed, but there is some kind of system failure before the commit happened. Then you can roll back to the
Uh, so,
initial state or
so,
whatever save points you have.
so how does that exactly happen? I mean, I'm trying to understand, like, if a system failures, so you lose the values in the memory, I mean, the buffer
No,
space.
see, what happens is that when a system failure happened, okay, let's say some 50 rupees was taken out from A's account, then it was supposed to go into B's account. Okay. But after the 50 rupees was taken out from A's account, before B's account could be updated, the system failed. So at this point, I will issue a rollback statement which will go back to the initial state of the database where A had that 50 rupees in his account, where I hadn't yet taken out the 50 rupees. So it will go back to initial state. So that is the last consistent state basically.
So, which means the transactions that happened between the last commit and the system failure, that will be stored somewhere, is it?
No, there is no commit. No commit has been issued. Only that is why that the rollback can happen. If there is a commit, then I cannot issue any rollback.
Yeah. So, say, assume, just before transaction one, there was a commit happen. So now a transaction one comes, and there is another transaction, transaction two, and both are not yet committed. In between, there are some read and write operations, and middle of that, the system crash
So
happens.
T1 and T2 are two transactions which are concurrently running and none of them have committed, right?
Yeah.
And
So,
in some halfway, the system has failed.
right.
So in that case, you have to roll back both the transactions.
Will the okay?
See,
I'm
all this rolling back that is happening, na, these are there are log records, okay, which store
okay.
that what operations are happening. That is, this A is deducted by 50. This is
Oh,
stored in a log record. So
yeah,
these
that's
things will be
total.
discussed in week 11. Okay, log
Oh,
records are there.
okay. Yeah. Thank
Okay, that's why we can roll back. So rollback totally happens on this transaction logging based on that.
you. Okay. Yeah, got it. Thank you.
All right. Okay. So yeah.
Ma'am, regarding
Hmm.
this timestamp for this part of it, like you've not solved any questions, right? Would there be any like very
Yeah, yeah.
tough
See, yeah,
questions?
just check out. No, no, tough questions are not there. Just check out the PYQs. There are only a few types of question, one or two different types, and they are all
Okay,
based on whatever we discussed. Okay, nothing new is there.
okay, okay,
Okay, but if you face any difficulty in solving those, anyways, in next session we will discuss. But since the deadline is today, you can still post on Discourse. Okay.
okay. And one more thing, one very general question, ma'am. This all these now all these are back-end operations that we are discussing right now, right? So what and all like goes behind the this funds
Yeah, yeah.
transaction. So
The
like,
user
will
cannot
we
see this
be
thing.
using this in like Mad One project or something like that? Where will we be
Transactional things, I don't think you will be using.
we won't
But
be
yeah, there
okay.
will be there can be questions based on this. I think, like the basic, just if you know the concept or not, what is commit, what is rollback. These things might be there, but I don't think you have to perform anything, like write the code for
So
this.
we won't be using this information anywhere. Like I mean, we won't be implementing it as such, right? Is it?
I'm not sure if you implement this in Mad 1, Mad 2 projects. I'm not entirely sure, but I don't think you have to do this transaction logging thing because this is very difficult to implement. Not very easy thing.
Okay.
Okay,
Okay.
but
Okay.
yeah,
Okay.
obviously, if you go for a database administrator role later on, then
Obviously,
these
yeah,
will
yeah.
come into play.
Then this will be.
Yeah.
Okay, thank you. Yeah.
Okay, so what I will say is, since today is deadline, just go through PYQs and solve the questions on serializability. Okay, and this two-phase locking. So PYQ, even in, if you want to check out the previous sessions from last time, we discussed a lot of questions on this, what do we call it, two-phase locking protocol. Okay, I think it was in end-term revision session. Also, Piyush sir, I think, took one session on just solving numericals, so you can check out that question, that session also.
Okay,
Okay.
ma'am.
All right. So next class will start with week 11. Thanks for joining, everyone.
Thank you, ma'am.
Thank you, ma'am.
Yeah.
Thank you.
Ma'am, one more doubt.
Thank you, ma'am.
Week 11 deadline.
Week 11
Uh,
deadline will be extended, I think. Yeah.
okay. Thank you, ma'am.
Yeah.
Thank you.
Thanks.
Thank you.
Thank you.